If, at this very moment, you were to fire up the engines of the fastest ship ever built by human hands and aim it at the sun's nearest neighbor, it would take you 73,000 years to arrive. 73,000 years. That number is so staggeringly long that if the first modern humans, the ones who painted those first images on the walls of the Altamira caves, had launched that ship, it would still be on its long journey today, not even halfway there. Take a moment to let that sink in. Everything humanity has ever built, every civilization that has ever flourished and fallen, every empire that has risen and collapsed, all the brutal wars and world-changing revolutions, and all the great scientific discoveries, from the first fire to modern nuclear power, all of it fits into just a fraction of the time required for us to reach the nearest point in the universe outside our solar system, Proxima Centauri, a dim and cold red dwarf star. That star is a mere 4.24 light-years away from us. Yet, in practical terms, that distance is so vast it might as well be on the other side of the entire observable universe. But tonight, we will not be talking about the impossible. Tonight, we will explore something far more unsettling, because it turns out the question of how many light years a person can cross in a single generation leads to challenging answers that upend everything you thought you knew about the limits of physics. And some of those answers are so terrifying, you might wish you had never learned them. We will delve into 3 mysteries that modern science is only just beginning to understand. First, the mystery of speed, and why the universe seems specifically designed to keep us forever trapped on our little blue rock. Second, the proposed technologies to break out of that cosmic prison. Some are so radical they border on science fiction, while others are so feasible that various governments are already willing to fund their development. Third, the paradox of time that arises when we begin to move at relativistic speeds. This is a strange phenomenon that could allow a traveler to cross immense distances that, by all known laws, should be impossible to achieve in a single human lifetime. Tonight, you will discover something that will fundamentally change how you perceive space, something that will make you look up at the stars with very different eyes, and perhaps something that will keep you awake at night. Because when you truly understand the meaning of cosmic distances and what it takes to cross them, the universe ceases to be a wondrous place and begins to reveal its true nature, a breathtakingly vast, violent, and utterly indifferent emptiness. So indifferent that the mere fact we are here, wondering about these things, is something of a miracle. If you are fascinated by the deep mysteries of the cosmos, be sure to subscribe. Our journey begins now. The official version of space exploration sounds pleasant and full of hope. It tells us that humans are a species in constant expansion, that we have walked on the moon, sent probes to all the planets in our solar system, that we have rovers diligently exploring Mars, and that, eventually, we will colonize other worlds. Textbooks often present space as the next frontier, a territory we will conquer step by step, just as our ancestors once conquered the continents. First, Earth's orbit, then the Moon, then Mars, followed by the moons of Jupiter and Saturn. And finally, in a distant but achievable future, the stars themselves. However, there is a fundamental problem with this rosy narrative. It is completely false. Not that we are lying about our achievements in space, because those are real. We truly have done those extraordinary things. The problem lies in the extrapolation, in the idea that we can just keep pushing forward, gradually extending our reach over greater and greater distances. The reality is, there is a vast abyss separating the exploration of our solar system from reaching another star. It is an abyss not just in size, but of an entirely different order of magnitude. Let me illustrate this for you with numbers you've probably never heard put together. The Voyager 1 probe, launched in 1977, is the farthest man-made object from Earth. In more than 4 decades of tireless travel, it has covered a distance of about 23 billion kilometers. That may sound impressive, but in reality, that distance accounts for a mere 0.0006 light-years. To reach Proxima Centauri, Voyager 1 would have to multiply the distance it has already traveled by more than 7,000 times. Remember, it has been traveling for longer than most civilizations have existed. Voyager's speed is about 17 kilometers per second relative to the Sun. While fast by our terrestrial standards, this speed is pathetic when compared to the vast distances between stars. At that rate, as I mentioned at the beginning, the journey to the nearest star would take tens of thousands of years. Entire generations would be born, live, and die on that ship. Not one generation, not 10, but hundreds of generations, succeeding one another in the void. And this is where mainstream science tells us, for now, interstellar travel is impossible. We must accept that we can only explore our immediate cosmic neighborhood. Perhaps in a very distant future, with technologies we cannot even yet imagine, someone will find a way to cross these distances. But for now, the stars remain beyond our reach. That is the official version. And for decades, we have accepted it as an undeniable truth. However, the reality is much more complex and in some ways much darker, because it turns out there are specific technological proposals that could shorten the travel time to Proxima Centauri from 70,000 years to less than 20 years. Some of these proposals remain theoretical, others are being very actively funded, and at least one has passed proof-of-concept tests in laboratories right here on Earth. We are not talking about science fiction. We are talking about real physics, real engineering, and real money being poured into projects with a clear goal: to send something, whether a probe or eventually humans, to another star within this century. But this is the most unsettling part. When you start to study the details of these proposals, when you truly understand the underlying physics involved and the immense energy requirements, you realize something that space enthusiasts often prefer not to mention. To cross the distance between stars in a reasonable amount of time for a human, we would need to unleash a colossal amount of energy that would make even the most powerful nuclear weapons ever detonated look pale in comparison. We are talking about an energy level equivalent to the total output of our entire human civilization for many centuries, all focused on a single vehicle. And that raises some incredibly difficult questions for us. What kind of civilization would be capable of building something so monstrous? What would we humans do with that level of immense power in our hands? And what does it say about the nature of this universe that reaching for the stars requires us to master forces of almost unimaginable destruction? The history of space exploration has always been intimately tied to the history of war. The rockets that took us to the moon were developed from ballistic missiles. The satellites, mapping other planets, used technology derived from military spy systems. And the most promising proposals for interstellar travel, one way or another, all involve the manipulation of nuclear and subnuclear energies on a scale that would make any 20th century military strategist tremble. That isn't a coincidence. That is physics. The universe, in its most fundamental structure, demands a brutal price for speed. And that price is paid in joules, in gigatons, in quantities of energy that we normally associate only with apocalyptic destruction. Consider this. To accelerate a moderately sized spacecraft, let's say about 100 tons, to 10% of the speed of light, you would need an amount of energy equivalent to about 45,000 Hiroshima bombs. And remember, this energy isn't to destroy anything, but just to push the ship, to get it up to speed. And then you have to break it, which requires a similar amount of energy. We're talking about hundreds of thousands of nuclear explosions, directed with absolute precision, just to move an object the size of an apartment building. And 10% of the speed of light, while it sounds impressive, still means the journey to Proxima Centauri would take over 40 years. That's a one-way trip, and that number doesn't even account for the time needed to accelerate and decelerate. A young person, departing at age 25, would only arrive as they turn 65. And that's assuming everything works smoothly, perfectly, that there are no malfunctions, that the life support systems tirelessly keep the crew breathing for decades, and that the cosmic radiation shielding can protect them from the rain of high-energy particles that constantly bombards any object moving at such incredible speeds. And yet, even those 40 years, a generation spent on a journey through the cold between the stars, would be an unprecedented achievement in human history, because it would mean that, for the first time since we came into existence, a human could be born under one sun and close their eyes for the last time under another. It would prove that the immense distances we have considered for millennia to be utterly insurmountable could, at least in theory, be conquered within a single human lifetime. The question we will ponder more deeply tonight is not whether that is possible, but how much further we can go, because relativistic physics contains surprises that challenge our ordinary imagination. These are truths that show, under the right conditions, a traveler could cross not just the few light years separating us from Proxima Centauri, but far, far greater distances. There are distances that, from Earth's perspective, would take decades or even centuries to travel. But for the traveler themselves, as they move at near light speed, space and time would be compressed into a brief period, similar to a normal biological lifespan. This miraculous phenomenon is called time dilation, one of the strangest effects of special relativity that Einstein left to humanity. And although this phenomenon has been experimentally verified countless times, its profound implications for space travel are rarely discussed with the depth they truly deserve. Because when you start to crunch the numbers, you encounter results that seem to exist only in the pages of science fiction. Those results show that, theoretically, an astronaut could make a journey to the center of our galaxy and back within their own lifetime, while on their home planet of Earth, 50,000 years would have passed. That is not an exaggeration at all. It's real physics, and it is truly staggering to anyone who dares to contemplate it. But before we venture deeper into those mysterious realms, we need to understand the absolute basics. We need to understand why the speed of light is an unbreakable, absolute limit. Why can no amount of energy, no matter how immense, push an object with mass to that speed? And why, paradoxically, does the very limit that seems to imprison us in our tiny cosmic neighborhood hold within it the key to journeys that defy all our intuition about time? The story of the speed of light as a universal limit begins with a failed experiment. In the year 1887, two scientists, Albert Michelson and Edward Morley, attempted to measure the Earth's motion through the ether, a hypothetical substance that physicists at the time believed filled all of space and acted as a medium for light waves to travel through. Their experiment was designed with incredible sophistication and precision. They used a device called an interferometer to compare the speed of light in different directions, hoping to find the slightest variations that would reveal our movement through the cosmic ether. However, they found nothing. Absolutely nothing. The speed of light was exactly the same in every direction, no matter which way the Earth was moving. This null result, one of the most famous in the history of science, dealt a fatal blow to classical physics. Because if there was no ether, if light needed no physical medium to propagate, then something was profoundly wrong with our understanding of space and time. 18 years later, a young employee at the patent office in Bern, Switzerland, published a paper that solved this baffling mystery. Albert Einstein, then a complete unknown, proposed a radical idea. The speed of light in a vacuum is a constant for all observers, regardless of how they are moving. Whether you're rushing toward the light or trying to run away from it, whether the light source is approaching or receding, it no longer matters. You will always measure the exact same speed, down to the very number, 299,792 kilometers per second. This invariance of the speed of light had consequences that defied all common sense. Because if speed always remains the same, then other factors must change to compensate. Space must contract, time must dilate, and an object's mass must increase. The faster you move, the more pronounced these effects become. And as you approach the speed of light, they become infinite. Imagine you're on a constantly accelerating spaceship. At first, each time you want to increase your speed, you only need a certain amount of energy. But as you get closer to the speed of light, something strange begins to happen. Each additional kilometer per second requires a vastly greater amount of energy than the one before it. And the reason isn't that your engines are becoming less efficient, but that the ship's mass, from the perspective of an outside observer, is continuously getting heavier. At 90% of the speed of light, the ship's effective mass has more than doubled. At 99%, it has multiplied sevenfold. And at 99.9%, that mass has increased by more than 22 times. And here lies the dilemma. To accelerate a greater mass, you need more energy. But that energy itself has mass. And that additional mass also needs to be accelerated. It's an endless loop, and it becomes infinite precisely at the speed of light. To reach that threshold, you would need an infinite source of energy. And that, by definition, is impossible. This is the core reason why the speed of light is an absolute limit. It is not a technological barrier, nor is it due to a lack of imagination or resources. It is a fundamental property of the very fabric of this universe. Space-time is constructed in such a way that nothing with mass can ever reach that speed. There are no exceptions, no shortcuts, and no tricks, or at least, that's what we've always believed. Because, as it turns out, there are ways to bend the rules, ways to leverage the peculiarities of relativity to make journeys that, from a certain perspective, seem to violate the universe's speed limit. And although we are not talking about traveling faster than light in any real physical sense, the practical effect it delivers can be just as astonishing. The first peculiarity is the time dilation I mentioned earlier. But there are others. There is length contraction, which causes distances to shorten in the direction of motion. In addition, gravitational effects on time allow clocks at different gravitational potentials to run at different speeds. And there are even more far-out, speculative proposals, such as the Alcubierre drive, which could theoretically compress space in front of a ship and expand it behind, allowing for effective, faster-than-light travel without technically violating any limits. But the reality is much darker than the promising possibilities these theories suggest, because each strategy comes with an immense cost. Time dilation might let you experience less subjective time, but it does absolutely nothing to reduce the colossal energy needed to reach those relativistic speeds. And length contraction only applies from your perspective as the traveler. It doesn't change the actual distance the ship is forced to cross. And the Alcubierre bubbles, while they might be mathematically consistent, demand forms of negative energy that probably don't even exist in our universe. This leaves us with a brutal truth. In order to cross the staggering distances between stars within a finite human lifespan, we have no other option but to master energy sources on an apocalyptic scale. There won't be any clever shortcuts, and no magical solutions either. There is only the brutal physics of pushing a mass through the void, paid for in joules and with unforeseeable risks. And when we begin to put concrete numbers to the proposals for interstellar propulsion, the results are both inspiring and absolutely terrifying. Hopeful because they prove that the journey is, at least in principle, achievable, but terrifying because they reveal the precise kind of monstrous power we would be forced to master to make it happen. In the following sections, We will explore those proposals in detail, from solar sails that could reach 20% of the speed of light just by harnessing the pressure of radiation, to fusion engines that would burn helium-3 isotopes harvested from the very atmospheres of gas giant planets, from concepts for antimatter propulsion that could convert mass into pure energy with an absolute 100% efficiency, to generation ships where humanity would give up speed in exchange for creating self-sustaining ecosystems for hundreds of residents within. And in each case, we will run the numbers together. How much distance, how much time, and how many light years can be contained within a single generation? Because that question, however simple it may seem, holds answers that will completely change your understanding of the cosmos and our tiny place within it. The physics of space propulsion hides a mathematical truth that very few people outside of expert circles truly comprehend. There is a mathematical formula that silently dictates the fate of every journey into the endless void, known as the Tsiolkovsky rocket equation. It was laid down in the year 1903 by a Russian schoolteacher, a man who lived his entire life in obscurity and never once saw a real rocket take flight. Konstantin Tsiolkovsky, working in the solemn isolation of a provincial city, derived the fundamental relationship that governs all self-propelled movement in a vacuum. And yet, that equation, as elegant and simple as it is, acts as a death sentence for most of humanity's dreams of interstellar exploration. The equation shows that the final speed a ship can reach depends on only two factors. The first is the speed at which it ejects its propellant, what engineers call exhaust velocity or specific impulse. The second is the ratio between the ship's initial mass, when it's fully fueled, and its final mass after all of that energy has been spent. And the cruel heart of the matter here is the logarithmic relationship. That mathematical term carries a ruthless meaning. It means you get brutally diminishing returns. To double your ship's final velocity, you don't just need twice the fuel, you need to square the mass ratio. To triple the speed, you have to cube it, and so on, at an impossible scale. Very quickly, the amount of fuel required becomes absurd, then impossible, and eventually it surpasses the mass of our entire planet. Let's run a specific calculation to see just how severe this is. The best chemical engines we have today, like the kind that use liquid hydrogen and liquid oxygen, have an exhaust velocity of about 4.5 kilometers per second. To reach just 1% of the speed of light with this kind of propulsion, you would need a mass ratio so colossal that the initial ship would have to weigh more than the entire observable universe. This is not hyperbole for dramatic effect. It is the exact result of cold, hard mathematics. This explains why, to this day, not a single space mission has ever even approached relativistic speeds. Chemical rockets, no matter how much they are improved or refined, are fundamentally trapped by the physical limits of their combustion reactions. No matter how much money we throw at the problem, how many of the most talented engineers we hire, or how many decades we spend in tireless development, there is an absolute wall that chemistry can simply never overcome. However, chemistry is not the only path we can take toward the stars. Ion engines represent a promising leap forward in efficiency. Instead of burning fuel in the conventional way, this type of engine accelerates charged particles using electromagnetic fields, ejecting them out the back at a far greater velocity than any chemical reaction could ever achieve. NASA's Dawn probe, during its mission to explore the asteroid belt, used this kind of ion propulsion with xenon as its propellant. Its exhaust velocity reached around 30 kilometers per second. That's nearly 10 times better than the most powerful chemical rockets. But the biggest problem is the thrust. An ion engine produces an incredibly tiny amount of force, just a tiny fraction of a single Newton. To help you visualize it, imagine the thrust from the engine on the Dawn probe was about as gentle as the weight of a single sheet of paper resting in the palm of your hand. It might be enough to let the spacecraft accelerate slowly and patiently in the vacuum of space over many months, even years. But it's completely unsuitable for the quick acceleration required for manned missions or for hitting significant speed milestones in a short amount of time. On a more reasonable timeline, the concept of nuclear thermal propulsion offers a compelling balance. In this design, a nuclear reactor heats a propellant, usually hydrogen, and shoots it out at nearly double the velocity of traditional chemical rockets. NASA's Project Nerva, developed back in the 1960s, proved that these engines were completely viable. They actually worked. They were tested. But then, the program was regrettably cancelled. It became a victim of budget cuts and political anxieties surrounding nuclear safety. With nuclear thermal propulsion, a trip to Mars could be cut from 6 months down to just a few short weeks. However, when measured against the dream of interstellar travel, it's still not nearly enough. These improvements in exhaust velocity, as significant as they are, still can't change the ruthless reign of the Tsiolkovsky equation. We would still need mass ratios that are far too large, well beyond what our current engineering can handle. This is where the truly radical proposals come into play. Ideas willing to shed all conventional limits in order to harness the most pioneering physics. Fusion propulsion promises to deliver exhaust velocities reaching hundreds or even thousands of kilometers per second. Instead of simply heating a propellant with a reactor, these future engines would fuse light atoms like deuterium or helium-3, releasing a tremendous amount of energy and ejecting the fusion reaction products at near relativistic speeds. Project Daedalus, an audacious design study carried out by the British Interplanetary Society in the 1970s, proposed this exact vision: a colossal ship weighing 50,000 tons. This 50,000-ton ship would spend 4 years in constant acceleration to reach 12% of the speed of light, and was projected to arrive at Barnard's star after 50 long years. The numbers from the Daedalus project are truly sobering. To operate, the ship would need 30,000 tons of helium-3 for fuel. This is a gigantic amount, exceeding all known reserves on Earth by several orders of magnitude. This precious fuel would have to be harvested from the immense atmospheres of Jupiter or Saturn through massive, decades-long extraction operations. The sheer act of building the infrastructure needed to gather that fuel would represent an industrial undertaking, vaster than anything humankind has ever attempted in its entire history. And remember, Daedalus was just an unmanned probe. It carried no life support systems, no thick shielding against radiation, and didn't even have the ability to slow down once it reached its destination. It would simply glide past the target star system at a terrifying cruising speed, taking measurements for just a few short hours before disappearing forever into the silent interstellar void. For a manned mission, every requirement increases exponentially, like a mountain with no peak in sight. You need an enormous amount of additional mass to protect the crew and store their supplies. You need extremely durable backup systems that can operate reliably for decades. You need robust shielding to protect against cosmic radiation and dangerous collisions with interstellar dust. And most importantly, you need the ability to brake when you arrive. That means the ship must carry an enormous additional amount of fuel just for deceleration. However, that extra fuel needs to be accelerated along with the ship from the very beginning, which in turn increases the initial fuel requirement in a never-ending loop. Project Longshot, another study born from the Cold War era, attempted to solve some of these difficult problems. The project proposed a 400-ton probe, using a fusion reaction between helium-3 and deuterium to reach a velocity of 4.5% of the speed of light. The journey to the Alpha Centauri system would then take exactly 100 years. But unlike Daedalus, Longshot was designed with the ability to decelerate in order to safely enter orbit around the target star system. 100 years. That's an entire century of solitary travel just to reach the star nearest to us. That means the ship would be launched by one generation, monitored and managed remotely by the next, and its arrival would be welcomed by a third generation of people who had never even met those who drew the very first designs for the ship. This is a project that transcends the normal limits of a human lifetime. It requires uninterrupted organizational continuity and a sustained commitment from an entire civilization. Something that, until now, we as a species have never really proven we can maintain for that long. Now, let's take a quick look at Project Breakthrough Starshot, the most ambitious initiative currently in active development. This project received funding of up to $100 million from the Russian entrepreneur Yuri Milner, along with the enthusiastic support of great minds like the late Professor Stephen Hawking. Starshot proposes a completely different approach. Instead of building massive ships that carry their own engines, it would send thousands of tiny probes, each about the size of a postage stamp. These minuscule ships are equipped with sails made of ultra-thin material, and they would be accelerated by a massive ground-based laser array. The goal is to push them to 20% of the speed of light. At this astonishing speed, the journey to the star Proxima Centauri would take only about 20 years, which is well within a single human generation. For the first time in history, an object made by human hands could reach another star within the lifetime of the very people who designed it. The scientists who launched this mission, if luck smiles upon them, could very well live long enough to witness the first streams of data being transmitted back from a distant solar system with their own eyes. However, the accompanying technical challenges are immense. These probes, called star chips, weigh only a few grams. They would have to survive a massive acceleration, thousands of times Earth's gravity, in just the few short minutes the laser beam sweeps over them. These sails, only a few meters wide, would have to be woven from materials that don't even exist today. Materials capable of reflecting the laser light almost perfectly without absorbing heat or melting. And the laser array needed to provide that thrust would have to have a total power output of up to 100 gigawatts. To give you an idea, that number is equivalent to the entire power output of a medium-sized country, all concentrated into a single, focused beam aimed straight up at the sky. The laser power calculations have exposed the true scale of this challenge. To accelerate a sail weighing just 1 gram to 20% of the speed of light in 10 minutes, you need to impart it with a massive amount of energy, around 1 million joules. That number might not sound too overwhelming until you realize that the efficiency of energy transfer using radiation pressure is extremely low. Most of the laser's power would be lost due to reflection or scattering into the atmosphere. This massive system would need to generate and maintain that stable 100 gigawatt power level for each launch. And to ensure success, the plan is to launch thousands of these tiny probes, hoping that at least a few will survive the stormy journey to reach the final destination. And here, we touch upon a deeper issue, an aspect rarely mentioned in the enthusiastic presentations about this project. The Starshot probes will never be able to carry people. They are too small, too fragile, and too limited in every way. All those tiny ships can do is snap a few flyby photos and perform a few of the most basic measurements as they zoom past the Proxima Centauri system and then quietly transmit that data back to our dear Earth. The return journey for those signals will take another 4 long years, and the amount of information that a probe weighing a mere gram can collect and send across the vast interstellar distance is certainly extremely limited. Project Starshot is really just a first step, a device to demonstrate the technology and a proof that the concept can exist. It is by no means a complete solution for direct human exploration of the vast universe. To achieve that great feat, We need something much bigger, much more powerful, and vastly more ambitious. And this is where physics starts to get truly strange, far beyond what we normally imagine. There's a fascinating concept called antimatter propulsion. Antimatter is exactly what its name suggests, a type of matter composed of particles with the exact opposite charge of the normal particles we know. Imagine an anti-electron, also known as a positron. It has the same mass as a regular electron, but carries a positive charge. Or an antiproton, with the same mass as a proton, but a negative charge. When matter and antimatter accidentally come into contact, they instantly annihilate each other, converting their entire mass into the purest form of energy. According to the great equation of the scientist Einstein, the efficiency of this magical conversion process reaches an absolute 100%. Just 1 gram of antimatter annihilated with 1 gram of regular matter will release a horrific amount of energy, up to 90 trillion joules. To help you visualize that power, this amount of energy is equivalent to about 43 kilotons of TNT, which is twice as powerful as the atomic bomb that was dropped on Hiroshima, and it all comes from just 2 grams of material. An engine running on antimatter would have a theoretical exhaust velocity close to the speed of light. With a reasonable mass ratio, it could absolutely accelerate manned ships to significant fractions of the speed of light. A trip to the Alpha Centauri system could then be shortened to just a few decades or even a few short years, depending on the acceleration the passengers' bodies can withstand and the amount of precious antimatter we are willing to expend. However, there is always a problem, a hurdle so enormous that it could turn all these glorious promises into science fiction. At least for now, we still don't know how to produce antimatter in any significant quantity. The creation of antimatter on Earth is currently done mainly in huge particle accelerators like the one at the organization's CERN. The processes involved are extremely inefficient. To produce each gram of antimatter, one must expend a massive amount of energy, up to quintillions of joules, and the reality is, we have never produced a gram, but only microscopic nanogram quantities. In the entire history of CERN's operations, the total amount of antimatter created is not even enough to warm up a morning cup of coffee. For a manned interstellar mission powered by antimatter, we would need tons of this material. At our current level of technology, producing that quantity would require a colossal amount of energy, even greater than all the energy humanity has generated throughout its entire history. And that's not to mention, we still don't know how to store it safely. How do you handle a material that causes a catastrophic annihilation event with the slightest touch of ordinary matter? How do you channel it into a propulsion system under control? To date, antimatter remains in the realm of the theoretically possible, but practically, it seems completely out of reach. The same goes for even more outlandish proposals. For example, the Bussard ramjet, a visionary engine that would collect hydrogen from the sparse interstellar medium and perform fusion on the fly, thereby completely eliminating the need to carry heavy fuel. However, detailed analyses have shown that the drag created by scooping up hydrogen would likely exceed the thrust generated by fusion, accidentally turning the ship into a giant brake rather than an accelerator, or consider sails pushed by the radiation pressure from the sun itself. In theory, they could reach 1% of the speed of light if deployed close enough to our star. But at that speed, the journey to Proxima Centauri would still take more than 400 years, a period far too long for any conventional manned mission. And then there are the Alcubierre space-time warping bubbles I briefly mentioned earlier. They would require an amount of negative energy that might not even exist in our universe. Creating it, if possible, would involve a completely new kind of physics currently unknown to humanity. Science, when forced to honestly confront the question of interstellar travel, must admit an uncomfortable truth. We don't have any definitive answers. We only have proposals, calculations, and a cautious optimism mixed with well-founded skepticism. we still don't have a clear path from where we are to where we long to be. Every proposed technology carries with it fundamental limitations. Each seemingly viable solution gives rise to new, more difficult problems, and the scale of the challenge is so vast that it's sometimes hard to distinguish between ambitious engineering and pure fantasy. This doesn't mean interstellar travel is impossible. It simply means the journey requires monumental breakthroughs we haven't yet made. It means future generations will have to solve problems for which we don't even know how to ask the right questions today. It means that any prediction about when or how we will reach the stars must be met with immense humility. The numbers we can calculate with some certainty right now are these. With existing or developing technology, we could send tiny probes to the nearest star in about 20 or 30 years. With technology that is physically possible but requires many more decades of research, we could send larger ships, even manned ones, on journeys lasting from 50 to 100 years. And with technologies that seem like science fiction today but don't violate the known laws of physics, we could potentially shorten the trip to a matter of decades. However, in every scenario, we're still only talking about distances measured in a few scant light years. The nearest star, or perhaps the 10 or 20 closest neighbors, form a radius of exploration of about 25 or 30 light years around the Sun. Beyond that boundary, even the most optimistic proposals falter against the brutal reality of cosmic distance. Our Milky Way galaxy is 100,000 light years in diameter. The Virgo supercluster, the immense gravitational structure of which our galaxy is but a tiny member, is over 100 million light-years wide, and the entire observable universe stretches 93 billion light-years from end to end. Faced with these scales, humanity's most audacious ambitions seem strangely small and pathetic. We dream of reaching Alpha Centauri, but the universe responds with billions of distant galaxies we will likely never, ever set foot in. However, there is a crucial factor that these dry calculations have not yet included, a factor that could completely change the equation. It's a phenomenon so strange, so counterintuitive, that it feels more like a mystical spell than pure physics. Relativistic time dilation. Because it turns out that when you start moving at speeds approaching that of light, time itself behaves in ways no everyday imagination can predict. And it is this strange behavior that opens up possibilities that simple calculations of distance and speed cannot reveal. Possibilities that suggest the answer to our original question, how many light years can a human traverse in a single generation, could be much, much larger than any naive calculation might suggest. The year 1971 marked a major turning point in humanity's understanding of the flow of time. Joseph Hufferly and Richard Keating, two American physicists, conducted a bold experiment. They placed 4 cesium atomic clocks on commercial airliners and flew them around the world twice, once eastward, with the Earth's rotation, and once westward, against it. When those clocks returned and were compared to identical clocks that had remained stationary at the US Naval Observatory, a stunning truth was revealed. The times didn't match. The clocks that had diligently traveled through the sky had actually measured less time than the clocks that stayed still on the ground. The difference was incredibly small, measured in mere nanoseconds, but it was real, it was measurable, and it perfectly matched the genius predictions of Einstein's theory of relativity. This experiment, now widely known as the Hufferly-Keating experiment, was the first direct proof that time does not pass the same for everyone. It proved that speed and gravity can indeed affect the rate at which clocks tick. That if one of 2 identical twins stayed home while the other took a high-speed journey, they would age at completely different rates. This is not a figure of speech, nor is it a sensory illusion. It's real physics quietly at work in our world every day. The global positioning system you use on your phone every day is the most vivid proof. Its accuracy depends entirely on this branch of physics. GPS satellites orbit the Earth at about 14,000 kilometers per hour at an altitude of about 20,000 kilometers. Due to their high speed, the atomic clocks on the satellites run slower than clocks on the ground by about 7 microseconds per day, according to special relativity. However, because they are farther from Earth's center of mass and experience weaker gravity, their clocks tend to run faster by about 45 microseconds per day, according to general relativity. The net result is that the clocks on the satellites run faster than clocks on the planet's surface by about 38 microseconds each day. If these tiny discrepancies weren't meticulously corrected, positioning errors would accumulate at a rate of about 10 kilometers per day. After just 1 week, the entire GPS system would become completely useless. Every time you look up directions on your phone, you are actually benefiting from relativistic corrections calculated with extreme precision. Einstein, though he likely never knew it at the time, was helping modern humans find the shortest way home. Every time you hold your phone in your hand to find your way, you're actually benefiting from incredibly precise relativistic corrections. Einstein, though he probably had no idea during his lifetime, helped you find the shortest path to the nearest restaurant. Yet, these effects we see in our daily lives are just faint whispers compared to what really happens at relativistic speeds. As an object approaches the speed of light, time dilation is no longer a laboratory curiosity. It becomes the dominant factor governing the traveler's entire experience. The formula that governs this phenomenon, while mathematically elegant and simple, is staggering in its consequences. This dilation factor is called gamma, and it is equal to 1 divided by the square root of 1 minus the velocity squared divided by the speed of light squared. At the slow speeds we experience daily, this factor is effectively just 1, and time dilation is imperceptible. But as speed begins to increase, gamma increases with it, and as it approaches the speed of light, it grows towards infinity. Let's consider a few specific examples to see this strange relationship clearly. At 10% of the speed of light, the gamma factor is approximately 1.005. This means that for every year that passes for the traveler, 1 year and 2 days have passed back home on Earth. This is a very small difference, almost unnoticeable. At 50% the speed of light, the gamma factor increases to 1.15. For every year the traveler experiences, nearly 14 months have passed on Earth. We begin to feel the separation. At 80% the speed of light, the gamma factor reaches 1.67. At this point, for every subjective year on the ship, 20 months have passed back home. A 5-year mission for the astronaut would mean more than 8 long years of waiting for their family. At 90%, the speed of light, the gamma factor is 2.29. Each year for the traveler corresponds to more than 2 years on Earth. A subjective 10-year round trip would mean that upon return, 23 years have passed on Earth. At 99% the speed of light, the gamma factor leaps to 7.09. 7 years on Earth are equivalent to just 1 year for the interstellar traveler. Just imagine, an astronaut leaves at age 30 and travels for 10 subjective years. When they return, their biological age is only 40. But back on Earth, all their friends from the same generation have already turned 100, and this is where things get truly extraordinary. At 99.9% the speed of light, the gamma factor is 22.4. Each year for the traveler is equivalent to more than 2 decades on their home planet. At 99.99% the speed of light, the gamma factor reaches 70.7. That means 70 years pass in just 1 subjective year. At 99.999% the speed of light, the gamma factor exceeds 223. More than 2 centuries will pass on Earth for every year the traveler experiences. Do you see where this is leading? Imagine a ship capable of accelerating at a constant rate, exactly equal to the acceleration you feel standing on the ground. This level of acceleration would be incredibly comfortable for the crew, allowing them to feel their normal body weight throughout the journey. The ship would accelerate for the first half of the journey to reach near light speed, then turn around and decelerate for the second half to stop at its destination. With this itinerary, the calculations yield results that defy all intuition. A trip to Proxima Centauri, 4.2 light-years away, would only take about 3.5 years of the traveler's subjective time. Meanwhile, on Earth, about 6 years would have passed. A trip to the star Vega, 25 light-years away, would take about 6.5 subjective years. On Earth, 27 years would have faded into the past. A trip to the very center of our galaxy, 26,000 light-years away, would cost only about 20 subjective years. But on Earth, 26,000 years would have gone by. Even a trip to the Andromeda Galaxy, 2.5 million light-years away, would only take about 28 subjective years for those on board. How can a person traverse 26,000 light-years in just 20 years? Are we moving faster than light? The answer is no. What changes here is not speed, but the experience of time and space. For the traveler, space contracts and time is compressed. The universe seems to shrink around the ship as it accelerates. Distances that seem insurmountable from an earthly perspective become within reach for someone moving at relativistic speeds. This is the magical combination of time dilation and length contraction. However, this door to the stars does not open for free. It demands a devastating price, turning the dream of travel into a nightmare of both engineering and survival. The first obstacle is energy. To accelerate a crewed ship to a speed where time dilation becomes significant, we need an amount of energy that challenges all scales of human understanding. Let's do a calculation. Consider a modest ship weighing 1,000 tons, equivalent to the size of a small frigate. To push it to 90% the speed of light, we would need to give it a kinetic energy of about 4 times 10 to the 22nd joules. That's 40 sextillion joules. To put that in perspective, the total energy output of all humanity in an entire year is only about 6 times 10 to the 20th joules. This means we would need 60 years of the entire world's energy output just to accelerate that ship, and then an equal amount to break it. This figure doesn't even account for efficiency losses, energy for life support systems, or the recycling of water and air, and that's just for 90% the speed of light. If we really want to benefit from time bending at the 99% level, the energy requirement increases more than threefold. At 99.9%, it increases by more than tenfold. These numbers become so absurd, they're almost laughable. Currently, no imaginable energy source could provide this level of power, not even fusion or antimatter. Even if we assume that the energy problem has been solved by some transcendent future civilization, other brutal dangers remain. Interstellar space is not a perfect vacuum. It contains an average of about 1 hydrogen atom per cubic centimeter. At normal speeds, this is nothing to worry about. But at relativistic speeds, that thin gas transforms into a deadly stream of radiation. Every hydrogen atom the ship encounters will collide with an energy proportional to the square of its speed. At 50% the speed of light, each proton hitting the hull carries the energy equivalent of high-energy cosmic radiation. We're not talking about a few sparse particles, but billions of impacts per square centimeter every single second. At 90% the speed of light, this energy increases tenfold. The ship would be like it's sitting in the middle of a continuous nuclear explosion. To protect the crew, we would need shields meters thick made of special materials, but the weight of this armor would only exacerbate the initial energy problem. And then there's dust. The interstellar medium contains microscopic dust particles, from carbon grains to tiny ice fragments. At relativistic speeds, they become projectiles with apocalyptic destructive force. A dust particle weighing just 1 microgram, colliding at 90% the speed of light, would release the energy equivalent of several kilograms of explosives. Over a journey of many light years, the ship would have to endure billions of such impacts. They would erode the ship's surface, destroy optical systems, blind communication devices, and just one impact on a critical component would be enough to end the entire mission instantly. To deal with this devastating dust and radiation, scientists have dreamed of ambitious solutions. These include powerful magnetic shields to deflect charged particles, or sacrificial hulls that wrap the ship, designed to be eroded away instead of the main structure. People have also considered ships shaped like a slender needle to minimize the contact surface area, or even using powerful laser systems to vaporize dust particles just before they hit the hull. However, each of these solutions, when added, brings with it stacks of new complications, increasing mass and opening up countless other possibilities for failure. And then, there is a more subtle, but no less dangerous problem: the relativistic Doppler effect on the cosmic microwave background radiation. You see, our entire universe is bathed in a faint microwave radiation, an echo left over from the Big Bang. This radiation has cooled to a temperature of only about 2.7 degrees above absolute zero. To us now, or to any spacecraft moving at normal speeds, this radiation is completely harmless and benign. However, everything is turned upside down when you venture into relativistic speeds. The Doppler effect will compress the wavelength of the microwave radiation in front of you in your direction of travel. At 90% the speed of light, the gentle microwaves from the front will be compressed into X-rays, and when you reach the 99% threshold, they will become gamma rays, the most energetic and dangerous type of radiation. At this point, your ship is no longer gliding peacefully. It is plowing headfirst into a cascade of high-energy radiation, pouring down from the entire sky in front of you. The intensity of this torrent will grow ever more fierce as you accelerate. At the 99% speed of light threshold, without a dense and perfect shield, a traveler would receive a lethal dose of radiation in just a few short hours. The vast universe, the very thing we yearn to explore, now becomes a furious enemy, attacking us from all directions with energy accumulated over its own billions of years of history. In principle, none of these barriers are insurmountable, but when combined, they form a set of engineering challenges so formidable that they completely dwarf any grand construction project humanity has ever undertaken. Imagine with me what it would take to build a ship capable of taking humans to true relativistic speeds. The hull would have to be forged to withstand the continuous impact of high-energy particles and space dust for decades. It would have to be self-healing, or possess redundant layers of armor that could be replaced mid-journey. Massive propulsion systems would have to operate reliably for years on end, without a single minor failure, because any interruption during acceleration or deceleration would mean death for the entire crew or a catastrophic failure for the entire mission. The necessary redundancy would multiply the ship's total mass many times over, perhaps even tens of times over. And then, the life support system would have to perform a nearly impossible task, recycling water, air, and all nutrients with an absolute efficiency of 99.99% or higher for decades. Even the smallest cumulative loss over the years would be enough to deplete the ship's vital reserves. The food production system would also have to operate flawlessly in a harsh radiation environment, perhaps under constant acceleration to create artificial gravity, keeping the human body from wasting away. But perhaps the greatest challenge lies within the human spirit itself. The crew would have to face and survive the most extreme isolation anyone in history has ever experienced. For years, or even decades, they would be confined to a cramped space in the midst of a vast void, with no chance of rescue, no real-time communication with their home, Earth. They would have to live with the haunting knowledge that every passing moment pushes them further and further away from everything they have ever loved and known. An engineer designing such a mission would have to anticipate thousands, tens of thousands of potential failure modes to build in redundancies. Its complexity would be orders of magnitude greater than any previous engineering project. And the most terrifying part is that we have no way to test it beforehand. You can't simulate a decades-long relativistic journey right here on the ground. We would be forced to place our entire faith in mathematical models, in extrapolations, then launch the ship and pray that everything works as designed. Here, the margin for error is absolutely zero. We are facing a challenge that transcends the scope of conventional engineering, entering a realm that some call meta-engineering or civilization-scale engineering. These are projects that demand the combined resources of an entire nation or even of all humanity. They are projects that could take generations to complete, requiring a consistency of purpose that human society has never before demonstrated in its history. Yet, as difficult as it is, none of this violates the laws of physics. Every barrier has a conceivable solution. The final question remains: will we ever be capable of making them a reality? Meanwhile, the dangers of high-speed interstellar travel remind us of a truth we often try to forget. This universe was not designed for human beings. It is not a gentle amusement park waiting for us to enjoy. It is an absolutely hostile environment, where the mere act of surviving and moving through it requires us to master sources of energy and matter that we do not yet possess. And when we finally do, if that day ever comes, we will have to confront even more disturbing truths. Truths about the inherent violence of the cosmos and the terrible price of moving through its vastness. Because, it turns out, the immense energy required for interstellar travel is not merely an engineering challenge. It also carries the potential to become a weapon of planetary-scale destruction, one that any starfaring civilization would undoubtedly possess. This opens up haunting questions about the silence of the universe that you might not want to consider. Consider this: a spacecraft moving at 90%, the speed of light, carries an enormous kinetic energy, equivalent to 4 billion Hiroshima bombs for every single kilogram of its mass. A modest ship weighing just 1,000 tons, traveling at that speed, would contain more destructive power than the entire nuclear arsenal accumulated during the Cold War, multiplied 1,000 times over. And if that ship were to accidentally or intentionally collide with a planet, it would release that entire horrifying amount of energy in a fraction of a second. The result would be absolute extinction. Not the kind of partial extinction often seen, where a few species might luckily survive. We are talking about the complete sterilization of a world. Its oceans would vaporize in an instant. The planetary crust would melt into rivers of magma, and the entire biosphere would be transformed into a superheated ball of plasma, expanding into the depths of space. This is an uncomfortable truth, a topic rarely discussed in the enthusiastic stories of our journey to the stars. Any technology powerful enough to take us to distant suns is, by definition, also a technology of planetary-scale mass destruction. You cannot have the power without the potential for devastation. Physics does not allow it. When a massive object moves at near-light speed, it automatically becomes the most terrifying weapon of mass destruction the human imagination can conceive. It doesn't need explosives, nor does it require complex nuclear warheads. The sheer power of its motion, its kinetic energy alone, is enough to wipe out an entire civilization. And unlike a nuclear missile, which we might hope to intercept or deflect, a relativistic projectile gives us no practical warning. At 90% the speed of light, the object would arrive just seconds after its light reached our eyes. There would be no time to evacuate, no time to react, only instant, absolute, and silent annihilation. Military strategists have quietly contemplated this scenario for decades. It's known as a relativistic kinetic weapon, or more commonly, a relativistic bomb. And that is precisely why some theorists suggest that the terrifying silence of the universe, the absence of the extraterrestrial civilizations we've been searching for, may have a much darker explanation than mere distance. But before delving into that frightening implication, we need to understand the scale of violence that already exists in this universe. Because it turns out, the cosmos is already filled with destructive events that can make humanity's worst nuclear nightmares seem small and insignificant. These are events that are constantly happening in every direction. We are protected by vast distances, but that protection is not guaranteed to last forever. On March 19, 2008, at 6:12 a.m. Coordinated Universal Time, a pulse of gamma radiation silently swept past the Earth. NASA's Swift satellite detected it and immediately aimed all its instruments towards the source. What it found challenged all human scales of understanding. At a distance of 7.5 billion light-years, a massive star had collapsed. In its final moments, before becoming a black hole, it focused a portion of its terrifying collapse energy into two beams of gamma rays, fired in opposite directions. And by a strange coincidence of cosmic fate, one of those beams was aimed directly at our tiny blue planet. The event, designated GRB 080319b, was so bright that it was visible to the naked eye for about 30 seconds for anyone who happened to be looking towards the constellation Boldest at that moment. Just imagine that. Visible to the naked eye from a distance of 7.5 billion light-years. That's a distance of nearly half the radius of the entire observable universe. To give you a sense of this power, if a similar event were to occur just 1,000 light-years away, right here in our own galaxy, that gamma-ray beam would completely destroy Earth's protective ozone layer in a matter of seconds. Then, devastating ultraviolet rays from the sun would pour down onto the planet's surface, unshielded. Every food chain would collapse, and crops would fail completely. And that would only be the beginning of the tragedy. If this disaster happened at a distance of just 100 light-years, the radiation would be intense enough to severely burn any creature exposed to the night sky. The oceans would even begin to boil in the regions directly beneath the event's focal point. And if you shorten the distance to just 10 light-years, it would be a total extinction, a complete annihilation, not just of a small part of the biosphere. Gamma-ray bursts, or GRBs for short, are the single most powerful explosions in the universe since the Big Bang. In just a fraction of a second, they can release more energy than our sun will emit over its entire 10 billion-year lifespan. Although the most catastrophic bursts are rare, they are still happening out there. Every day, scientists detect several new bursts from different, distant points in the vast cosmos. We are constantly bathed in their distant echoes, but thankfully, we're protected by the sheer, vast expanse of space that separates us from them. However, that vastness is not an eternal, impenetrable shield, because right here, in our own galaxy, there are stars that hold the potential to create gamma-ray bursts when they reach the end of their lives. Eta Carinae, a blue supergiant star located about 7,500 light-years away from us, is one of the top contenders on this dangerous list. It possesses a colossal mass, more than 100 times that of the Sun, and is currently in the final stages of its stellar evolution. When it explodes, and it most certainly will explode, it could generate a gamma-ray burst. The good news for us is that this star's axis of rotation is not currently pointed towards Earth. You see, gamma-ray bursts are highly directional, focusing their power into narrow jets. If Eta Carinae were to collapse, humanity would likely just witness a spectacular supernova show in the sky, rather than suffer a direct, lethal blast of radiation. The bad news, however, is that we still don't know about all the potentially dangerous stars in our own galactic neighborhood. Thick clouds of interstellar dust obscure vast regions of the Milky Way. Who knows? There could be dozens of ticking stellar time bombs aimed directly at us, completely unbeknownst to us. Besides, ordinary supernovae, even without the gamma rays, are just as terrifying if they occur close enough. The brightest supernova ever recorded in human history exploded in the year 1054 in the constellation Taurus. Ancient astronomers from China and the Arab world to Japan documented this event in meticulous detail. For weeks, it was visible in broad daylight, and for months afterward, it dominated the entire night sky. That star was 6,500 light-years away from us. What we observe today in that location is the Crab Nebula, the ever-expanding remnant of that ancient explosion. It is still shining, with the leftover energy from a cosmic cataclysm, a battle that released more energy in a few seconds than our sun will in its entire lifetime. Let's assume a similar supernova occurred at a distance of only 50 light-years. The consequences for us would be incredibly severe. At 25 light-years, it would truly become a global catastrophe, and at just 10 light-years, it would undoubtedly be the end of all complex life on this green planet. Some scientific theories suggest that the Great Ordovician-Silurian extinction event, which took place about 445 million years ago, when up to 85% of all marine species suddenly vanished, may have been caused by a distant gamma-ray burst. The evidence we have so far is only circumstantial, but it aligns in a deeply unsettling way. The extinction patterns from that era perfectly match what we would predict from a devastating irradiation from above the atmosphere. Organisms living in the surface layers of the water were the most heavily devastated, while those living deep on the ocean floor were, fortunately, better protected. Gamma rays don't leave behind craters or specific chemical residues that we can use for definitive proof. If it really did happen, the only remaining evidence is the pattern of death preserved in the fossil record. And heartbreakingly, that pattern fits unnervingly well. However, cosmic radiation is not the only violent threat hiding in the silent vacuum. There are also physical objects moving through space with enough energy to reshape an entire world. On June 30th, 1908, at 7:17 a.m. local time, something exploded with a deafening roar over the remote Tunguska region of Siberia. That terrifying blast flattened 80 million trees over an area of 2,000 square kilometers. The shock waves from this event were recorded by seismic instruments all around the globe. Witnesses hundreds of kilometers away described a flash of light brighter than the sun and a horrific sound like the end of the world. Strangely, no crater was ever found, nor were any significant fragments discovered at the scene. For decades, the Tunguska event remained a profound mystery, sparking countless theories from antimatter to even alien spacecraft. Today, science believes it was likely a small asteroid or a comet nucleus with a diameter of 50 to 80 meters that detonated in the atmosphere at an altitude of 5 to 10 kilometers. The immense friction with the air heated the object until the internal pressure exceeded its structural integrity, causing it to disintegrate into a massive fireball, carrying the energy equivalent of about 10 to 15 megatons of TNT. 15 megatons. That's 1,000 times the power of the bomb dropped on Hiroshima, and it all came from a rock just 80 meters wide. Did you know, if that Tunguska event had occurred just about 4 hours and 52 minutes later, the Earth's rotation would have placed the city of St. Petersburg, then the capital of the Russian Empire, Directly under the meteorite's entry path, a city with over 1,500,000 residents would have been wiped off the map. The history of the 20th century would have certainly taken an entirely different, unforeseeable path. And yet, Tunguska was just a minor event compared to what can really happen in the universe. 66 million years ago, a colossal asteroid, about 10 kilometers in diameter, slammed into what is now the Yucatan Peninsula in Mexico. The resulting crater from that impact, known as Chicxulub, is 150 kilometers wide. The energy released was equivalent to about 100 trillion tons of TNT, which is 1 billion times more powerful than the largest atomic bomb ever built by man. That devastating impact vaporized kilometers-deep layers of rock, creating tsunamis, hundreds of meters high, that swept across the coastlines of every continent on the globe. It incinerated forests on half the planet with a rain of molten debris. It ejected a massive amount of dust and soot into the atmosphere, blocking out the sun for years, halting photosynthesis, and causing a complete collapse of food chains across the Earth. The result was the extinction of 75% of all species on Earth, including the reign of the non-avian dinosaurs. A biosphere that had dominated the planet for over 150 million years was wiped out in just a few short months, paving the way for mammals, our distant ancestors, to finally have their chance to take control. According to calculations, this type of catastrophic impact occurs on average once every 100 million years. Statistically speaking, humanity seems to be overdue for the next one. But geological history has recorded events even more terrible than this. 252 million years ago, at the end of the Permian period, a catastrophe of unknown origin caused the extinction of 96% of all marine species and 70% of all terrestrial species. It was the largest mass extinction in the history of life, chillingly known as the Great Dying. Although the exact cause is still debated, with the prime suspect being massive volcanic eruptions in Siberia that lasted for millions of years, some researchers do not rule out the possibility of an asteroid impact even larger than the Faun Chicxulub event. The oceans became acidified, global temperatures soared by more than 10 degrees, and atmospheric oxygen levels dropped to a point almost incapable of supporting life. It took Earth 10 million years to recover. 10 million years. That is a vast, yawning chasm of time that no species could consciously endure. During that period, only bacteria and a few simple organisms carried the faint memory of a previously thriving world. Everything else had to start over again from absolute zero. And this is where the violence of the cosmos connects directly to our initial question about interstellar travel, because it turns out that a ship moving at relativistic speeds, from a physics perspective, is no different than a giant asteroid in terms of its impact energy. A 1,000-ton ship traveling at 90% the speed of light would, if it were to strike the Earth, release more energy than the Chicxulub asteroid, and a larger ship, or one moving faster, could easily carry energy equivalent to or even greater than the eruptions that caused the Permian extinction. In other words, any civilization capable of interstellar travel automatically possesses the ability to wipe out all life on a planet. This isn't a side effect, nor is it an accident. It's an inevitable consequence of the physics required to propel a ship at high speeds. A standard interstellar cargo ship, used to transport goods between colonies, would become a planet-destroying weapon if aimed directly at an inhabited world. It wouldn't need any modifications, nor would it need auxiliary weapons. It would only need to change its course. This painful realization has profound implications for how we think about extraterrestrial civilizations and the famous silence of the vast universe. In 1950, during a lunch with colleagues at Los Alamos, the physicist Enrico Fermi posed an immortal question as the conversation turned to the topic of flying saucers and alien life. After considering the billions of stars in the galaxy, the billions of years for intelligent life to emerge, and the apparent ease with which life arose here on Earth, Fermi asked, "Where is everybody?" This question, now known as the Fermi paradox, has puzzled the greatest minds for over 70 years. If technological civilizations are indeed common, and if interstellar travel is possible, no matter how difficult, then the galaxy should be teeming with signals, probes, colonies, and countless pieces of evidence of intelligent activity. And yet, we see nothing. The sky remains utterly silent. We seem to be alone in a universe that, by all calculations, should be bustling with life. Dozens of explanations for this paradox have been proposed. Perhaps intelligent life is extremely rare. Perhaps civilizations self-destruct before reaching the stars. Or perhaps they exist, but are intentionally avoiding contact with us. Perhaps intelligent life is something exceedingly rare in this cosmos. Perhaps civilizations destroy themselves before they can reach for the distant stars. Perhaps they still exist somewhere, but are trying to avoid all contact with us. Or perhaps we are simply searching in the wrong way. However, there's one explanation rarely discussed openly, perhaps because its implications are too disturbing to contemplate comfortably. It's known as the dark forest hypothesis. Imagine you are a civilization that has just developed the capability for interstellar travel. You know for certain that other civilizations might also exist in this vast galaxy. You know that you can never predict whether their intentions are good or evil. And you understand clearly that any ship they send your way is, in essence, a weapon capable of completely destroying your world. In that situation, what would you do? The most logical answer, however terrifying it sounds, is to strike first. Destroy any civilization you happen to discover before they have the chance to destroy you, and at the same time, maintain absolute silence to avoid being detected by other hunters who are thinking the exact same thing. In this haunting scenario, the universe is like a dark forest, filled with armed hunters. Everyone moves in absolute silence, listening intently for the slightest sound, and is ready to fire at the first sign of other life. The silence of the universe we observe, then, is not evidence of loneliness, but an expression of profound fear. It's a galaxy-wide Cold War, where no one dares to speak, because to speak is to sign your own death warrant. This is a speculative hypothesis, and we cannot prove or disprove it with current data. However, it is strangely consistent with physics and explains the terrifying silence of the night sky, as well as the complete absence of civilizations in our vicinity. This carries a very heavy implication. Every time we send a signal into space, every time we broadcast a message of our presence, we may be inadvertently inviting our own extinction. The active search for extraterrestrial intelligence, instead of being a noble and hopeful scientific endeavor, could be the most dangerous act humanity has ever undertaken in its history. If one day we actually detect a clear signal from another civilization, the most appropriate response might not be to reply enthusiastically, but to maintain absolute silence, or perhaps something even worse. Interstellar travel, the dream that has inspired us for generations, may not be a wondrous adventure of discovery, but an entrance to a brutal cosmic battlefield, where the only rule is a simple one: kill or be killed. Of course, these hypotheses could be entirely wrong. The galaxy might truly be empty and peaceful. The silence out there could simply be because we are not yet advanced enough to recognize the greetings. We could genuinely be the first, or the only ones, in existence. But that ignorance, combined with the fact that interstellar travel requires us to master destructive energies, forces us to pause and reflect deeply. Besides the dangers from other civilizations, there is another form of cosmic violence, one that requires no hostile intent, but arises simply from the laws of the universe operating over immense timescales. Our galaxy, the Milky Way, is currently on a collision course with the Andromeda Galaxy. In about 4.5 billion years, these two giant spiral galaxies will begin the process of merging. It will be a grand dance that lasts for billions more years. Although individual stars will probably not collide directly due to the vast empty space between them, the orbits of everything will be chaotically disrupted. Solar systems could be flung out into the cold of intergalactic space or thrown directly towards the supermassive black holes that reside at the centers of both galaxies. Our dear Earth, if it still exists by then, could face any of these fates. We could be ejected into deep space, far from any source of heat, until the entire planet freezes over forever in darkness. Or we could be swallowed by a black hole, disappearing forever behind the event horizon. While none of this will happen within a human lifetime, it illustrates a fundamental truth. The universe is not static, not safe, and not designed for permanence. Everything is changing, colliding, destroying, and regenerating on scales beyond human comprehension. We are just lucky to be living in a temporary lull, a rare moment of stability that allows complex life to emerge and persist. But that moment is finite, and the great forces will eventually bring it to an end, non-negotiably. What we can say for certain is this: interstellar travel fast enough to compress time into a single human generation requires us to master energies on a catastrophic scale. Those energies could wipe out an entire world as easily as we delete a file on a computer today. And that brings us to a concept that defines the absolute limit to our future existence. It's called the cosmic horizon. This is the boundary beyond which no signal, no ship, and no traveler can ever reach us, no matter how advanced our technology becomes or how long we wait. That horizon is currently about 16 billion light-years away from us and is constantly receding, not because it is moving through space, but because space itself is expanding. With every passing second, regions of the universe that are theoretically reachable today cross that threshold and vanish from humanity's grasp forever. Entire galaxies, each containing hundreds of billions of stars and countless planets, are silently slipping into eternal oblivion. No technology, whether it's a warp bubble, a wormhole, or an antimatter engine, can compete with the speed at which reality itself is being stretched apart. We are trapped on a small, shrinking island of causality, in the middle of a vast ocean of possibilities that are moving away faster than we can ever chase them. This is the greatest paradox of interstellar travel. Even if we solve every technical problem, we are still mercilessly limited by the very laws of the universe. Our universe is not only expanding, it is also slowly cooling down. Over timescales so vast they defy all understanding, everything will gradually fade to black. Cosmologists divide the future of the universe into different eras. The current epoch, the one we are living in, is called the stelliferous era. This is an age dominated by stars, diligently burning hydrogen to illuminate the universe. This era will last for about 100 trillion years, a number so large it's almost impossible to comprehend. But compared to what comes after, it is merely a blink of an eye in the void. When the hydrogen is depleted, when the last star flickers out, the universe will enter darker and colder eras, leading to an ultimate heat death, where no energy differentials exist, no complexity, and no possibility for life or consciousness. When the universe's hydrogen runs dry, when the last star is born and then fades into nothingness, the degenerate era will officially begin. White dwarfs, the corpses of gentle stars like our sun, will gradually cool toward absolute zero. Neutron stars will radiate their last vestiges of energy into the silent void. At this point, black holes will dominate the cosmic landscape, silently devouring what little matter remains within their reach. This era will last for an almost unimaginably long time, 10 to the 40th power years. Try to picture it, that's the number 1, followed by 40 zeros. This number is greater than the number of atoms that make up your body, greater than the number of grains of sand on all the beaches of Earth, multiplied by the number of stars in the entire observable universe. But even that domination will eventually come to an end. Black holes, entities that seem eternal, turn out not to be. The physicist Stephen Hawking proved in the 1970s that they emit a subtle form of radiation, causing them to gradually lose mass over time. Small black holes will evaporate in a cosmologically short time. Supermassive black holes, like the one that reigns at the center of our galaxy, will take much longer. But finally, after 10 to the 100th power years, that is, the number 1, followed by 100 zeros, the last black hole in the universe will evaporate in a quiet whisper of particles. What remains will be a nearly perfect void, photons scattered light years apart, electrons and positrons occasionally moving at an infinitesimally slow pace. No more structure, no more complexity, no more possibility for life, for consciousness, or for any thought. All that is left is the final thermal equilibrium, also known as the heat death of the universe. It is a state of maximum entropy, where nothing can ever happen again because there are no energy differentials left to drive change. This is the fate that physics predicts for all existence. It's not a remote possibility, nor is it a vague speculation. It is the inevitable consequence of the laws that govern our universe when projected into the distant future. And it is here that the central paradox of existence arises. We are alive right now. We are conscious right now, in a pitifully brief moment between the Big Bang and the heat death. We exist in this fleeting instant of cosmic history, where stars still shine and planets can still harbor liquid oceans, where complex molecules can assemble into structures capable of wondering about their own existence. What does this truly mean? Some would say it means nothing at all. They believe we are just random chemical accidents in a purposeless universe, that our consciousness is just an insignificant side effect, a temporary bubble of complexity that will dissolve into the final thermal chaos. For them, the very question, what does it mean, is meaningless, because meaning is just a human-made construct imposed on a reality that inherently contains none. This view, known as cosmic nihilism, carries a cold and irrefutable logic. The universe existed for 13.8 billion years before intelligent life appeared on Earth, and it will continue to exist for trillions of years after we are gone. Our existence is a statistical blip, a tiny fluctuation in a vast system that neither needs nor notices us. And yet, there is another way to look at it. Consider this. In the entire observable universe, with its 2 trillion galaxies and its trillions upon trillions of stars, we have yet to find any evidence of another conscious mind. No artificial radio signals, no alien megastructures, no patterns indicating that intelligence is manipulating matter on a scale we could detect. This could mean that intelligent life is incredibly rare, so rare that we might be the only ones in the entire vastness of the cosmos, or at least the only ones in the region of the universe we can reach. If this is true, then our existence carries an entirely different weight. We are not an endlessly repeated accident. We are something unique. Perhaps we are the only way the universe can know itself, the only collection of atoms that can contemplate the whole and ask what it all means. The physicist Freeman Dyson once hauntingly expressed this idea. The universe knew we were coming, not in a mystical sense, but in the sense that the fundamental physical constants, the forces that govern matter, seem to be perfectly fine-tuned to allow for the existence of complexity, of chemistry, and of life. If the strong nuclear force were just a little different, atomic nuclei would never be stable. If the electromagnetic constant changed slightly, molecules couldn't form. If gravity was stronger, stars would burn through their fuel too quickly for life to evolve. If it were weaker, stars would never ignite their nuclear furnaces. This miraculous fine-tuning has led some physicists to propose the anthropic principle, the idea that we observe a universe compatible with life, simply because only in such a universe could we exist to observe it. While this might seem like circular reasoning, it holds a profound truth about the relationship between the observer and the observed. We exist in a universe that permits our presence, and perhaps we are the only ones who can witness that universe in all its terrible beauty. This perspective completely changes the question of interstellar travel. It's no longer just a story of exploration, survival, or mere scientific curiosity. It touches on something more fundamental: the possibility that we are the only ones who can carry the spark of consciousness beyond this fragile planet. Our expansion to the stars is not a luxury or a wild ambition, but a cosmic responsibility. Because if we are unique, then the extinction of humanity would not just be our tragedy, but an irreplaceable loss for the universe itself. It would be the extinguishing of the only light of consciousness in a vast, unthinking ocean of darkness. In philosophy, there is a concept called the veil of ignorance. Imagine you don't know where you would be in this universe. You don't know if you'll be an atom in a distant star, a speck of dust in intergalactic space, or a conscious being on a habitable planet. From that perspective, what kind of universe would you hope for? The answer is probably a universe where consciousness has a chance to flourish and expand. A universe where nascent minds are not condemned to death on their home planets. A universe where interstellar travel is possible, however difficult, and strangely enough, that is exactly the kind of universe we appear to live in. The distances between stars are immense, but not infinite. The speed of light is a limit, but not an absolute prohibition, thanks to time dilation. The energy required for relativistic travel is enormous, but within the grasp of nuclear fusion, all the obstacles we've considered are formidable, but in principle, they are all surmountable. It's as if the universe has given us a perfectly calibrated challenge, not so easy that we would solve it before we had matured as a species, but not so difficult as to be impossible for an advanced civilization. The effort to overcome that challenge will transform us into something better, something more worthy of the stars. This might just be a coincidence, but it's such a remarkable one that some thinkers believe there's something in the structure of the cosmos that favors the expansion of conscious complexity. This idea, sometimes called the strong anthropic principle or teleological cosmology, while controversial and difficult to test, offers an answer to the existential angst we feel when we confront our own smallness. Perhaps we are not small at all, perhaps we are the very opposite. But another paradox arises when we think about interstellar travel on the scale of an entire civilization: the deep time paradox. Let's assume humanity can survive the next 1,000 years without destroying itself. Let's assume we finally master interstellar technology and begin colonizing other star systems. How long would it take us to fill the entire Milky Way? The calculations yield a surprisingly modest number, even moving at just 1% of the speed of light. With each colony taking 1,000 years to stabilize, the entire galaxy could be colonized in less than 10 million years. 10 million years might sound like an enormous amount of time to humans, but our galaxy is over 13 billion years old. Any civilization that arose in the first few billion years would have had more than enough time to expand to every corner of the Milky Way. Yet, we see no evidence of that expansion. We haven't found any alien artifacts right here in our own solar system. This silence brings us back to another, perhaps more unsettling possibility. We might be the first. This is called the dawn hypothesis, which suggests that Earth is the first place where life has had enough time and stability to develop technological intelligence. If this is true, we are the absolute pioneers, the first to look up and try to cross the abyss, to carry consciousness beyond its home world. To this day, we have yet to detect any signals from great megastructures around neighboring stars. The night sky remains absolutely silent. One possible explanation we've mentioned, the dark forest hypothesis, is that civilizations may have destroyed each other or chosen to hide in the darkness out of primal fear. However, there is another explanation, just as plausible but perhaps even more profound. Maybe we are the first. Statistically, that sounds unlikely, given the enormous number of stars and the age of the universe. But what if we are the first to reach the threshold of interstellar travel? This idea is known by a poetic name, the Dawn Hypothesis. It suggests that the conditions for intelligent life to emerge are so specific, dependent on a chain of incredibly precise astrophysical and biological events, that they have not yet been met anywhere else in this vast galaxy until now. Perhaps Earth, with its unique history of violent asteroid bombardments, frigid ice ages, mass extinctions, and resilient recoveries, is the first place where life has had enough time and stability to evolve to the level of technological intelligence. If this is true, then the silence of the universe out there is not evidence of danger or eternal loneliness. It is simply the silence of a universe patiently waiting to be awakened. In that case, we would be the absolute pioneers, the first beings to look up and wonder what awaits among the stars. We are the first to attempt to cross the vast abyss, carrying the flame of consciousness away from our home world. This possibility carries an almost unbearable weight of responsibility. If we are truly the first, then our every action or inaction in the coming centuries will determine the entire future of consciousness in this galaxy. If we happen to destroy ourselves, it might take billions more years for another species to have a chance to try again. Or perhaps it will never happen at all. However, if we succeed, if we manage to expand, survive, and eventually colonize other star systems, then humanity will become the ancestor of all that is to come. All civilizations, all cultures, all forms of life and thought that blossom in the Milky Way for billions of years to come will have originated from us, here and now. It's hard to imagine a greater stake. Some would argue that all of this is distant and irrelevant to them, that what happens in millions of years has no meaning for their individual lives, which last only a few short decades. They believe we should focus on the problems at hand, on short-term survival and daily happiness, and let the distant future take care of itself. This viewpoint has a certain practical logic, but it inadvertently ignores something central to human nature. We are the only known species capable of thinking about the distant future, of imagining what will happen after we die and acting now to influence it. This ability of temporal projection is perhaps humanity's most brilliant characteristic. When we plant a tree whose shade we will never enjoy, we are practicing this ability. When we write books for readers who have not yet been born, we are practicing this ability. When we persistently invest in education, science, and infrastructure for the benefit of future generations, we are practicing this ability. The journey of interstellar travel is, after all, just the logical extension of that same forward-looking tendency. It is the cosmic version of planting a tree. We don't do it for our own individual benefit. We do it because we are the kind of creature that can imagine a better world and constantly strive to create it, even if we ourselves will never live to see the final destination. And perhaps that is the solution to the paradox of our insignificance in the face of infinite space. We are not important because we occupy some privileged position, but because we can choose to become important. We are important because we can embrace the indifferent vastness of the universe and decide to give it meaning. We can look up at the stars and silently promise, we will get there, no matter how many generations it takes, no matter the unimaginable sacrifices. Meaning is not something that is readily available for us to find in the universe. Meaning is something that we ourselves create and project onto it. That act of will, in the face of infinite emptiness, is perhaps the only true form of transcendence available to finite beings like us in an infinite universe. However, there is one final paradox we are forced to confront, a paradox that arises from the very foundations of physics: temporal exile. Remember the numbers we calculated together. A traveler moving at a constant acceleration could cross the galaxy in a few decades of their own subjective time. But on Earth, during that same journey, 26,000 years will have passed. This has a painful implication. Any astronaut who undertakes an interstellar journey at relativistic speeds is not only leaving their home behind in space, but is also permanently leaving it behind in time. Imagine you set off for a star 20 light-years away. That round trip might take only 10 years of your life, but when you return, 40 years will have passed on Earth. Everyone you once loved is now 2 decades older, or perhaps they are gone. Society has changed in ways you cannot possibly imagine. The Earth you left has ceased to exist forever. For longer journeys, the time discrepancy becomes absolute. A traveler to the galactic center would return to find an Earth so different that even its name would no longer be remembered. Entire civilizations would have been born and died during their absence. Perhaps humanity itself would have vanished. The traveler would be like a ghost from a distant past, as lost as a Homo erectus suddenly appearing in a modern, brightly lit metropolis. This is the true price of the dream of interstellar travel. Not just the enormous energy, not just the deadly radiation, but a permanent exile from humanity's timeline. You would have to leave behind not only your loved ones, but the entire historical era to which you belong, to become a stranger on your own planet. Some would argue that this makes manned space travel undesirable. They think no sane person would choose to give up everything they belong to for a destination that promises nothing better. But others see the issue very differently. They see the journey not as a loss, but as a liberation, a way to escape the death that binds us to a specific era. It is the only opportunity to see the future with one's own eyes, even if it is a future where there is no longer a place for them. And perhaps for a certain type of person, that is enough. The promise of seeing strange stars, of setting foot on worlds untouched by human hands, of being present, even for a moment, in a distant future. Perhaps they would be willing to pay the price of temporal exile without a moment's hesitation. If such people exist, if humanity can produce such radical explorers, then the journey to the stars will always have a future. It will not happen as an organized project of an entire civilization, but as a series of courageous, individual leaps into the unknown. Each traveler will be a lone pioneer, leaving everything behind to touch infinity. Maybe we don't need to colonize the entire galaxy to prove our existence. Maybe all it takes is for a few of us, the boldest, or perhaps the craziest, to choose to venture out toward the stars, knowing they could never come home. Because in the end, interstellar travel isn't really about arriving at any specific destination. It's about proving that we can try, that humanity is not completely trapped, that the indifferent vastness of the universe cannot contain us if we choose freedom. That act of asserting will against the immense void is the meaning we've always sought, a meaning not to be given, but to be seized by minds that refuse to settle for the mundane. Will that be enough? Can a meaning we create for ourselves compensate for the lack of a preordained purpose in the cosmos? Maybe, maybe not, but it's all we have. Tonight, we've come a long way, from the dry confines of the Tsiolkovsky rocket equation to the terror of relativistic radiation, from time dilation to agonizing existential paradoxes. Together, we've calculated energies that defy imagination and distances that dishearten even the strongest of spirits. But now is the time to connect these disparate threads, to see the bigger picture that emerges when all the pieces are put in their place. The question that has guided us on this journey seems simple enough. How many vast light years can a single human lifetime cross? And the answer, as we've seen, depends entirely on what we're willing to trade and what we're willing to sacrifice. With our current technology, the answer is painfully realistic. Virtually none. The fastest ships we possess would take tens of thousands of years just to reach the nearest star. A human generation, typically defined as 25 or 30 years, is only long enough for us to inch forward a minuscule fraction of that immense journey. In reality, we are still completely motionless in the vast cosmic ocean. However, with technologies being diligently developed, like the light sails in the Breakthrough Starshot project, we could send tiny probes at speeds up to 20% of the speed of light. These small emissaries could cross about 5 or 6 light years within a human lifetime. That's enough to reach 2 or 3 of the nearest star systems, enough to send back the very first images of planets orbiting other suns. Still, it's not enough to carry humans or even our most sophisticated research equipment. If we look at plausible but undeveloped technologies, such as the fusion propulsion engines of Project Daedalus, we could launch massive ships at 10 to 15% of the speed of light. In that case, our exploratory reach would extend to about 10 or 15 light years in a single generation. Dozens of star systems would be within reach, including worlds we believe could potentially harbor life, but the cost is immense. The travelers on that ship must accept the fact that they might die in transit, or arrive only when their hair has turned gray. With speculative technologies that are far more advanced, but still consistent with the laws of physics, like antimatter engines or advanced fusion drives, we could reach speeds where time dilation begins to reveal its true power. At 50% of the speed of light, a subjective 30 years on board would allow us to cross about 20 light years. On our dear Earth, however, nearly 40 years will have passed. At 80%, a traveler's 30 years would correspond to about 40 light years, while back home, 50 years would have slipped into the past. And with technologies that we now consider science fiction, but which violate no known laws of physics, if a ship could maintain a constant acceleration of 1g for years, the distance it could cover would become astounding. In a single lifetime, a traveler could cross hundreds of light years. After several generations, they could even traverse the entire galaxy. But upon their return, they would find an Earth so changed it would no longer be recognizable as home. The spectrum of what's possible ranges from around 0 to hundreds of light years, from absolute stillness to irreversible temporal exile, from the safety of the present to the perils of extreme progress. Yet, these numbers, as impressive as they are, fail to capture the whole truth, because interstellar travel isn't just a tale of distance and time. It's a story of transformation. It's about what we would have to become to achieve such great feats, about what we would lose and what we would gain on the journey. Consider a civilization capable of sending humans to the stars on relativistic ships that can compress time. Such a civilization must have mastered energy production and storage on a scale we now only see in stars themselves. They would have to build magnificent structures in space, dwarfing any project on Earth. They would have to solve extreme survival challenges to keep a crew healthy for decades. They would have to forge materials capable of withstanding conditions no material today can endure. Most importantly, that civilization would have to achieve a level of social coordination and multi-generational cohesion that no human society in history has ever demonstrated. In other words, the people who set out to explore the stars will no longer be the civilization we know today. It would be a different entity, one that has evolved not just technologically, but socially, politically, and perhaps even biologically, Some futurists have speculated that the true interstellar travelers might not be biological humans at all. They could be artificial intelligences, minds uploaded to digital substrates that have no need for oxygen, water, or gravity. These beings could power themselves down for centuries, reactivating only upon arrival, without suffering the degradation of an organic body. They would be immune to deadly radiation, indifferent to the bone-chilling cold of space, and completely free from the needs that make manned space travel so incredibly difficult. If this vision is true, then the answer to our original question changes completely. The number of light years a human can cross in a generation would no longer matter as much as the distance their digital descendants could cross in their long sleep. But there is something hollow and unsatisfying about that answer. Because when we ask how far we can go, we aren't really asking about the abstract entities of the future. We are asking about ourselves, these creatures of flesh and blood, filled with curiosity, desire, and fear. We want to know about the experience of looking through a ship's window and seeing an alien sun for the first time, about the emotional weight of setting foot on land that no ancestor had ever known. We want ourselves, or something close enough to us, to be there, to feel that the connection is real. And this is where physics must meet philosophy. Time dilation poses profound questions about our identity. If you travel fast enough for time to be compressed, where your 30 years correspond to 300 years on Earth, you are still physically yourself. Your atoms, your memories, and your stream of consciousness remain intact. But socially and emotionally, you have become a complete stranger. No one would know who you are. No one would share your old historical context. You are like a visitor from a distant past, which to those living would be as opaque as the Stone Age is to us today. This form of relative immortality comes at a cost, measured not in energy, but in connection. Every light year you cross further severs you from the tapestry of humanity. Eventually, you would be the last witness to an era no one else remembers. You become a conscious ghost, wandering through a future that is not your own. Some would see this as a profound tragedy, others as the ultimate liberation. Whichever way you see it, this physical reality points to one thing. The colonization of the galaxy will not happen as the uniform expansion of an empire. It will happen as a fragmentation. Each colony will be an isolated island, separated not just by light years of empty space, but by centuries, even millennia, of time. Each branch of humanity will evolve independently, developing its own unique cultures and biologies, until the very concept of human no longer has a single, unified meaning. In a million years, descendants on opposite ends of the galaxy could be as different from each other as we are from chimpanzees today. The evolutionary pressures of alien worlds will mold them in ways we cannot possibly predict. And although they all share a common root from 21st century Earth, that connection will eventually fade into distant myth. This isn't necessarily a bad thing, because diversification is a survival strategy. The more variations of intelligence that exist scattered throughout the galaxy, the lower the risk of complete extinction. A catastrophe on one planet won't be able to end it all. The picture that emerges isn't a unified galactic federation like in Star Trek, but an archipelago of time. These are islands of consciousness, separated by deep oceans of time and space. Each island will write its own history and define its own meaning of life. And we, the people of today, will become the mythical ancestors to them all. We will be as distant as the skeleton of our ancient mother, Lucy, is to us now. Perhaps we will be remembered, studied, but never truly understood by minds that have evolved so far beyond our own. There's a strange and proud form of immortality in that legacy. This is not the immortality of the individual, the kind we often crave in moments when the fear of death suddenly rushes in, but the perpetuity of our lineage, our influence, and our deepest origins. We are the ones laying the first stone for a journey without an end, the seeds for the diversification of consciousness in this universe, a proliferation that will last as long as the universe itself exists. Is this form of transcendence enough to soothe the individual fear of death, or the final dissolution of all that we know? There is no objective answer to that question. It is entirely a matter of values, of character, and of what each of us chooses to believe is meaningful. Some will find comfort and solace in the idea that some part of us will live on forever. Others will see it as merely an illusion, a self-deception to mask the brutal truth of our finite human lives. But perhaps the most important thing isn't whether that answer is comforting enough for us. Perhaps the real question we should be asking is, what do we choose to do with the brief time we have? Because no matter what happens millions of years from now, whether we colonize the galaxy or vanish forever on this planet, every decision we make right now will have consequences. The technologies we tirelessly develop, the institutions we build together, and the good values we pass on to future generations. All of these things are quietly shaping the future in ways we cannot possibly foresee, but they are completely real, and the very fact that we are here together, contemplating distances of light years and timelines of millions of years, says something incredibly important about our nature. We are creatures who carry within us the ability to imagine the seemingly impossible, who can feel awe at cosmic scales that far exceed our everyday experience. We can question our place in a vast universe that owes us no answers. This capacity for wonder and relentless questioning is perhaps humanity's most precious inheritance. It is more valuable than any advanced technology, more enduring than any great empire, and more meaningful than any achievement we can measure. It is this magical ability that has driven us to look up at the twinkling stars and wonder how to reach them. Not necessarily for its practicality, as most of us will never see an interstellar ship with our own eyes, let alone ride on one to undertake a journey of 1,000 leagues. Yet, that very question has transformed us profoundly. It forces us to expand our thinking beyond the trivialities of personal life, compelling us to confront the immensity of existence and find a way to reconcile with it. That question forces us to choose whether this universe is a prison that confines humanity or an enticing invitation. And that decision, the way we choose to interpret the world, is perhaps the most real thing we possess. Let's return to our original question one more time. How many light years can a human travel in a single generation? We have seen the technical answers. They range from 0 to hundreds of light years, depending on the technology we assume. However, there is another answer, one that cannot be measured in kilometers, in years, or in units of energy like joules. In just one generation, we have come a long way. From believing the Earth was the center of the universe to clearly understanding that we are merely orbiting an ordinary star in the suburbs of a very ordinary galaxy. In just one generation, we have stopped seeing the stars as lifeless, fixed points of light, and come to understand that they are brilliant suns, just like our own, orbited by countless planets. We have developed the ability to detect those planets, to tirelessly study their atmospheres, and to constantly search for the faintest traces of life on worlds tens of light years away. Over the past generation, although our physical bodies of flesh and bone have not moved even a single light year, we have truly expanded our consciousness across the visible galaxy. Perhaps that is the true meaning of star travel. It is not simply physical displacement, something that could take millennia to fully develop, but the expansion of the mind, the ability to embrace what was once considered unreachable, to comprehend what was once beyond our perception. And then, in a single quiet moment, we feel that the vastness of the universe is not a terrifying threat, but rather something like a shared home. In a way, we have already reached the stars. not with our physical bodies, but with something far more important, with imagination, with burning curiosity, and with that deep part of our soul that refuses to accept any limit as final, that refuses to see a boundary as something that cannot be crossed. The stars out there are still very far, absurdly far, so far that it seems even the laws of physics are conspiring to keep us forever separate from them. However, they are no longer strange, no longer absolute mysteries that make us tremble. We now understand what they are, how they work, and why they shine so brilliantly. We know that out there are planets with liquid oceans and breathable atmospheres. We understand how arduous this journey is, but it is not impossible, and that awareness changes everything. Because as long as even the smallest possibility exists, even if it requires centuries or millennia to develop, even if it involves sacrifices we cannot yet imagine, then we are not truly trapped. We are not condemned to be chained to this planet until the sun expands and swallows it, or until some asteroid destroys everything. We always have a way out. We have a future that extends beyond the boundaries of Earth, far beyond the solar system, and past every limit we once believed was absolute. And that provides a kind of freedom, not the freedom to go wherever we want, whenever we want, because that may never exist. But it's the freedom of knowing that there is still so much ahead, that this vast universe is not empty of opportunities, and that humanity's story does not have to end here. Tonight, we have journeyed very far. Even though our bodies have remained perfectly still, we have contemplated distances that humble the imagination and timelines that stretch beyond the normal experience of a human life. We have bravely faced the ferocity of the cosmos and understood our fragile place in it all. We have asked about the meaning of existence in an indifferent universe, only to realize that meaning is something we weave ourselves, not something we wait to find. And now, as peaceful sleep draws near, I have just one last thing I want to share with you. Look up at the sky if you can, not right now, as you're probably about to drift off. But tomorrow, or on some clear night, step outside and gaze at those twinkling stars. Every tiny point of light you see is actually a brilliant sun, and each of those suns might have worlds of its own, holding stories that we may never fully comprehend. And though the distances out there are infinite, though their scales defy all human comprehension, those tiny points of light are still directly connected to you through the very fabric of spacetime that holds your body right now. They are part of the same universe as you. The very universe that made you is the one that shaped those stars. You are never separate from the stars, because you are a part of them. Literally, every atom in your body was forged inside the core of a brilliant star. Billions of years ago, the iron in the blood flowing through your heart, the calcium in your bones, and the oxygen you're breathing, all of it came from stars that exploded long before our own sun was formed. You are stardust that has learned to admire its own origins. You are a part of the universe, questioning its own existence, and that question, that very act of contemplation, is perhaps the most extraordinary phenomenon in all of existence. You don't need to travel to the stars to connect with them, because that bond has always been there. You have always belonged. But perhaps, one day in the future, our descendants will truly make that great journey. They will cross the light years that seem untouchable to us today. They will set foot on worlds lit by suns that, to you tonight, are just tiny specks in the night sky. And when they arrive in those distant places, they will carry a part of you with them. Not your memories, not your personality, but something much deeper, more fundamental. They will carry the boundless curiosity that drove you to ask how far we could go. They will carry the burning desire that made you look up. They will carry the spark of consciousness that was kindled on this blue planet. And if we are lucky enough, that flame will spread across the vast expanse of the galaxy. That is the true meaning of being human. It doesn't lie in the limits we face, but in our refusal to accept them as final. It's not in the distances that separate us, but in the fierce longing to cross them. It is not in the certainty of death, but in the conviction that some precious part of us must endure. And with these thoughts, let sleep gently find you. The stars will continue to twinkle while you are sound asleep. The universe will continue to expand in its beautiful indifference. And tomorrow, when you wake, you will still be an inseparable part of it. You will still be stardust admiring itself, still a great question with no final answer. And you know what? That is perfectly okay, because perhaps the question itself is more valuable than any single answer. Perhaps wondering how many light years we can cross is more important than knowing the exact number. Maybe this great journey began long ago, the day our ancestors first looked up and wondered what those shimmering lights were. And perhaps that journey will never end. Sleep well. May the starlight illuminate your dreams, and tomorrow, may you continue to find the courage to ask your questions.